is our 7th episode, and it will be our first episode in chapter 5. However, I borrowed this episode from the end of chapter 3, the last part of chapter 4, the last part of chapter 4, in order to be a ground for us, a solid ground for us to continue chapter 5. This chapter is about the relative mass of atoms and molecules, which is chapter 4 actually. But this part is invited to become our main thing before we start chapter 5. It starts with 3 main items for both core and supplement, is to describe relative atomic mass A, as the average mass of the isotopes of an element concepts to 1/12 of the mass of an atom of carbon 12. Define relative molecular mass mR as the sum of the relative atomic mass, relative formula mass, and will be unit for ionic compounds. Calculating reacting masses in simple proportions calculations will not involve the mole concept. So the mole concept is going to be the coming concepts. But for this, we are going just to study this. And today we are going to start this. So be careful and be with us so we can go forward and do something that is very good for all of us. Let us go and see what is happening. Okay, when we start to weigh something, we always relate this something to another thing. So we can say that, for example, your tall is twice the tall of XYZ, or your tall is the X, while his tall is Y. So we compare things together. Putting in mind that we have the atom or a molecule or even an ionic formula, all these, when you weigh them, they are very tiny. You can't weigh them using the ordinary ways. So what they do, they dig their minds, all the chemists and scientists, they dig their minds and come out with something that is reasonable to weigh things together. So what they do, they calculate all the weights of the or observe all the behavior of the atoms, and they come out with a result that carbon 12, the isotope carbon 12, is the best example of a weighing substance. We can rely on him in order to come out with how we can weigh atoms. So what we have is that the carbon 12 weight is 12 because it's related to its atomic mass. So based on this, we find that the hydrogen atom is 1/12 to it. And then we try to compare all of these things to it. So when we say relative atomic mass, we will just say a relative atomic mass is the average weighted mass of an atom of an element compared to 1/12 the mass of the carbon 12 atom. Be careful about carbon 12 atom. Now, if we are talking about a molecule, we will say that a relative molecular mass is the average mass of a molecule of an element or a compound compared to 1/12 the mass of carbon 12 atom. So the 1/12 of the carbon mass of the carbon 12 is the unit of the relative mass. So the relative mass is, or the unit of the relative mass is the carbon atom. Here we are talking about the unit that makes you able to weigh other atoms. Now let us see here what is happening, and we are talking now about carbon 12 actually, and how carbon 12 is actually found or look like when we look to the periodic table. Here is carbon 12. You are going to find it this way. This is carbon 12. Here we have the 6, which is the atomic number, and the atomic number is the number of protons. You know that from the periodic table and how the elements of the periodic table are distributed. And then you are going to see another number here, which is the 12, below and down, which is the relative number or the relative atomic mass for the nearest whole number. And this comes from the number of proton plus the neutrons. So the number of protons and neutrons by itself, it make us know that the sum of them, the sum of the 6 and 6, will allow us to understand that here in the nucleus, you are going to see them here. The red one are the positive protons, while those without charge are the neutrons, and all of them are 12, and this is the number, and here is called the mass, the atomic number. But when we ask about the weight of the atom, it is the weight of the how we weigh. The weighing of the atom is the weighing of those 12 items, which are the 6 protons plus the 12 neutrons. So this is why they name it the relative atomic mass, not number. The number of both of them is 6 plus 6 equal 12. And this gives us the atomic number. But when we say the weight of them or weighing, their weighing is 12 also. And this is called the relative atomic mass. And this is why they choose the carbon 12 to be the measurement, the teeter of them, how we can measure them and measure other the relative atomic mass of any element is compared to relative atomic mass of carbon 12. Now, when we define the relative atomic mass, we compare it to the carbon 12, 1/12 of the carbon 12, the isotope carbon 12. But my point here, I would like you to be sure before we start calculations. Our definition is like this. Relative atomic mass is the weighted average of an atom of an element compared to 1/12 the mass of a carbon 12 atom. So, okay, now let us see this word, this term, weighted average, and ask ourselves a question: what is the difference between the regular arithmetic average or mean and the weighted average or mean? There is a big difference between the regular arithmetic average or mean and the weighted average or mean. We have to understand this very clearly, and we have to know where we are uh, stand. So let us go one by one and understand my point. Now, in this example, let us assume that we have a community, statistical community, and this community is formed of two categories, the males and females, and we have 16 female and 8 males. So actually that means the whole community is formed of 24 person, right? 8 plus 16 is 24. 16 female plus um, 8 males, the whole community will be 24 person, right? Correct. If we would like to get the regular mean, that means we need to make the regular mean the arithmetic mean, okay, or the arithmetic average. We just add both them together, so 16 plus 12, and we have only two categories, so we are going to divide them by 2, and this will allow us to come with a mean of 12. Correct? But this is not real when we talk about the contribution of each category in this community, because the females are actually 67% of this community, while the males are only 33%. So if we add another information, is that we would like the mean based on their contribution of this community. What we are going to do, we are going to see that the females multiplied by their abundance percent, that means their contribution in this community, plus the male multiplied by their abundance percent, which means abundance percent means the contribution of the category in this community, and then we divide them by 100. Why by 100, not by 2? Because the abundance is percent, abundance percent, so we have to divide them by 11 by calculation, and when we add 16 multiplied by 67 plus 8 multiplied by 33 over the total over 100, we are going to have a mean that representing contribution of each category in this community, and this is 13.36. That means now it is weighted average, because this average leans towards the category of the most contributed persons. females are more than males. So they have to, the mean should lean towards them. We have 16 female, so it becomes 13, which is more than the females, the more nearby the female total, while it is far away from the contribution of the males, which they are 8, and so it's more than 8, and this is why each one should contribute based on its abundance. An abundance percent means the contribution of the category on our statistical community. Let us go forward. If you do not understand what I'm saying, just pause it, pause the video, and try again and understand what I'm saying. If you want me to repeat what I'm saying in a different video, just let me know in the comments below. Based on our knowledge of knowing what is the difference between the regular arithmetic mean or average and the weighted mean or average, we would like to come out with an equation that solves the problem of any problem of relative atomic mass. And then the next video, we are going to do the same with the relative molecular mass. Okay, so and today we are just talking about the relative atomic mass. We don't go for the other masses. So in these calculations, we are going to say this is our equation, is the relative atomic mass, which is the acronym of it is AR, equal isotope 1 mass. So I'm going to look for the isotope 1 mass because I have different isotopes and I would like to come out with the average weighted mass for them. Okay, multiplied by isotope 1 abundance. That means the contribution of the isotope 1 in the community of this atom, plus isotope 2 mass multiplied by isotope 2 abundance percent. That means the contribution of isotope 2 in the this atom isotopes community. And also if it has 3, it's going to be isotope 3 mass multiplied by isotope 3 abundance percent till infinity, till n, over 100. Why 100? Because those abundance are in percent, so it should be divided by 100. Okay, for the relative atomic mass, there is, we can call it the unit, we can call it atomic mass unit, or you just put it without anything. Okay, we will deal with them when we go forward. So be careful about this equation, and we would like to apply this equation on a lot of examples so we can understand the concept of having the relative atomic mass and how we can calculate a relative atomic mass of isotopes. Now here we have 6 examples. We are going through them all and we will solve them. But before you look to the answer, I would like you to go and pause the video, try to take the problem itself and try to solve it. So the example 1 or problem 1 is to calculate the relative atomic mass of the following. Chlorine isotopes. We have only 2 chlorine isotopes, chlorine 35 and chlorine 37, and we would like you to bring or to calculate their atomic the relative atomic mass of these isotopes. Putting in mind that chlorine 35 is found in abundance of 75% and chlorine 37 in 25% in nature. And when we say abundance, we mean that the contribution of these isotopes in the total of the chlorine community. So we go and try to see that. First thing you have to do is to write down the equation that we already have. So our solution in the first step is to write the equation as it is, as we write it here. Isotope 1 mass multiplied by isotope 1 abundance, that means the percent, plus isotope 2 mass multiplied by isotope 2 mass abundance, and plus anything else, 3, 4, 5, whatever, how many, it doesn't matter how many isotopes that we have. But here we have only 2 isotopes, so we don't need from here. We just need 2 of them. So what we have is isotope 34, chlorine 35. So it is here the number 35 means the relative atomic weight of this isotope, which is the mass of this isotope, which is 35, multiplied by its abundance, which is the contribution of the chlorine 35 in the chlorine community, which is 75, plus number 2 isotope 2 mass, which is the 37, because 37 here is actually the mass of the number of proton plus the neutrons. So it is here, and multiplied by its abundance, which means the isotope 2 abundance, which is percent, it is 25, and the amount comes here, should be divided by 100. Why 100? Because this is a percent, so the number here is going to be 35.5%. Very simple, very direct. So be careful. It is easy thing. Do not disturb yourself. Pause the video and try to do it once and twice and 7 times in order to understand what is going on. Do not drop it. If you do not understand, write me down in the comments. Problem number 2 here is about thallium. We have 2 distinct isotopes of thallium. One of them is thallium 223 and the other one is thallium 225, and they have different contribution in the thallium community of them. So I mean different contribution. So the thallium 203 is found in abundance of 29.5%, while the 205 is in abundance of 70.5%. First step is to write down the full equation or formula. So the relative atomic mass of any isotope, and here is the thallium, is going to be isotope mass number 1 multiplied by isotope mass number 1, and isotope mass number 2 multiplied by isotope mass number 2. And since we have only 2, we don't need for the others, so we are going to multiply them by themselves. The 203 or the 203 is actually the relative the mass of the thallium isotope. So we put the mass of the isotope here and then multiplied by its abundance, which is 29.5%, plus the mass of the other, which is 205 or 205. So 205 is here, multiplied by its abundance, it is percent, it is contribution in the nature, and it is 70.5. The amount comes out from this math is just divided by 100. Again, why 100? Because this is a percent. So here is going to be 204.4%. And this tells you you can't add 203 plus 205 and comes out with, and divided by 2 and comes out with 204. No, it is wrong, because here we are going to ask about the weighted atomic mass average. And here we see that it leans towards 205 because 205 contributes more compared to the other one. 205 here contributes by 70%, while 203 contributes only by 29.5%. So the relative of the thallium is 204.4. Let us go. Now here we are going to calculate the relative atomic mass of the magnesium isotopes. Now here put in mind that magnesium has 3 isotopes, not 2. So what we are going to do is now we are going to see how we can bring 3 to the table, onto the table. So here the first thing is to write down your full relative atomic mass equation. So it is isotope 1 mass, isotope 1 abundance, and so on till the infinity or till n. Then we put it like this and then bring one by one. So we have 3 isotopes here. So first we are going to start with isotope 24. So it is 24 because this is the mass of the isotope, multiplied by it is percent or abundance. It is contribution in the community, in the statistical community, and this is, or the nature. So this is 79. So 24 multiplied by 79. The other one is 25, magnesium 25. So 25 is the mass of the this isotope multiplied by 10, which is it is contribution in nature. And then 26 multiplied by 11, because 26 is the mass of the isotope, the third isotope, and the 11 is the contribution of this one. And when we finish this mass, we just divided by 100. Why 100? Because this is a percent, and we are going to have this part, this result, which is 24.3. And be careful here, it leans towards 24 because it has the max, the big contribution, which is 75. So it is near the 24. 79% of it, of the magnesium in whole world means it is magnesium 25. And by this, by the way, we mean that if you pick one atom from anywhere in the world, 79% of the times it will be magnesium 24 isotopes. 10% of the times is going to be 25, magnesium 25 isotope, and 11 of the times might be or maybe magnesium 26 times. So consider this. First, pause the video and try to solve the problem by yourself, and then after that be sure go through our solution. Another example here, another example of 3 isotopes atom, which is the uranium. And we would like to solve the problem the same way that we solve the problem of magnesium. So calculate the relative atomic mass of the following, which is the uranium isotopes. We have three uranium isotopes, uranium 324 and 234 and 235 and 238. So we have three types, and they have different contribution. And actually, here we have a terrible type of contribution. Actually, an extreme contribution of uranium 238, which is 99.27% of the times is going to be, if you pick one uranium atom, it might be uranium 238 isotope. 0.72% of the times might be uranium 235, and 0.01 it will be uranium 234. Calculate this type of one. Now, what we are going to do here is actually we are going first of all to write down our equation. We don't care about the numbers here. The first step is to write down your the equation you are going to use. So this is the relative atomic mass, and you write the full equation. Then we come to compensate each part of it. Those are three items, so we are going to have three categories here. Relative of uranium equal 238 multiplied by 99.27 because this is the weight or the mass of the isotope, and this is the contribution of the isotope or the abundance of the isotope in nature. Now plus the other isotope, which is 235% multiplied by its contribution or abundance percent, and the third one the same thing. And when we make this calculation and divide it by 100, it's going to have 237.978. And I put the three digits here because I want you to understand how close this one to 238, because it is the abundance. 99.27% of the times, if you pick a uranium from any part of the world, it's going to be uranium 2038. And if we just round this, it's going to be 238. If we round those three numbers, and they deserve that, it's going to be 238. Be careful about this example and try to solve it several times and look at it and see what is going on. Pause, take it out, and try to make the calculation yourself. The fifth example is about copper and copper isotopes. So the copper isotopes, we have only two copper isotopes, and those are copper 63 and copper 65. And by 63 and 65, we say that 63 and 65 means the mass of each of them. And their distribution here is 69% for copper 63 or 63, and 31% for the copper 65. Now we are going to start a solution. The first thing is to do is to write down the equation, the suitable equation for your problem, and then you compensate of each one. We need two only, so we need this one and this one. We don't need the other one, so we are going to put them here, and then we compensate each one. This is the mass of the first one multiplied by its abundance, plus the mass of the second isotope multiplied by its abundance, And when we finish these calculations, divided by 100, it's going to be 36.6. And now it's again, it leans towards the 36 because it has the more abundance, the high contribution in the one. Pause again each one and try to solve it yourself without looking to our solution, and try to figure out where you are at. The sixth example, or the last example actually, is about the boron, which the boron has two isotopes, and we would like to know how to calculate the relative atomic mass for these boron isotopes. Again, calculate the relative atomic mass of boron and boron isotopes. We have only two boron isotopes, 10 and 11. So to your knowledge, boron 10 is found in 20%, while boron 11 in 80%. Those are only two, so we don't. First, as I told you before, you have to write this, the reasonable or the suitable or the correct equation, and when you do that, you just try to compensate here very directly. This was for the first one, so the isotope 1 mass is 10 multiplied by its abundance, which is 20. The mass of the second is 11, the multiplied by its abundance, and all of them over 100, and this comes with 10.8, and 10.8 is near 11, not and far from 10, so it leans towards the more contribution. The one that has this weighted average leans towards the element with the highest contribution in nature. Again, pause and do the calculations yourself. We come to our conclusion now. Now you know how to calculate the relative atomic mass of isotopes. Next time we are going to study how to calculate the relative molecular mass, and then the relative formula unit mass. We are going to do that, and one by one we are going with each other. Please do not hesitate. If you find any difficulty, just write me down in the comment section and let me know, even if you understand what I mean or not. And another advice I'm going to tell you is, when you come to the examples, first pause the after you understand it and you know how to do things, you pause them and try to solve them as problems, and then after that come to again to the example and see what is going on. Again, for the last time, do not hesitate. Ask me anytime. Have a good day and enjoy your time. Thank you for being with me. Bye-bye.